New Zealand, that's a picture of me on their $100 bill. I was born in 1871 on a farm in New Zealand. I was one of 12 kids and I was not pampered. Because I studied so hard, I was able to attend college under a scholarship, which was a big deal back in the day. To further extend my education, I traveled to the United Kingdom, where I became a research assistant for Professor J.J. Thomson. When I was with J.J. Thomson, I exhibited great excellence, and I discovered alpha and beta particles from uranium radiation. I also invented a detector for electromagnetic waves, such as magnetism, or radio waves, X-rays, or light rays, and so on. In Canada, I became a professor at the McGill University of Montreal. I continued my work in alpha and beta decays from uranium. This is the depiction of alpha and beta decay from the nucleus of atoms. I also discovered radioactive decay of substances, and in 1908 I was awarded the Nobel Prize, and we'll get to what those are a little bit later. But for now, radioactive decay is when one unstable substance decays and is transformed into another. So in this case, radium is decaying into lead when it emits alpha particles, which are helium nucleuses with two neutral charged particles, or neutrons, and two positively charged protons. And this is a positively charged particle, the alpha particle. And now a beta particle is a particle that is an electron, it's negative, and it's also emitted from the nucleus of an atom. So what happens is over time, the nucleus of an atom is chopped down into lead in this case. Anyway, I always joke that it was the quickest transformation I had ever witnessed, a physicist turning into a chemist. Many of my students received Nobel Prizes, such as Otto Hahn, a student who received his Nobel Prize in 1944 for atomic fission. Even though I was the first person to split an atom, atomic fission, Otto Hahn elaborated my discovery. Moving on. I was a professor of physics in the United Kingdom at the University of Manchester and the University of Cambridge. My prior mentor and professor, J.J. Thomson, proposed a model of the atom called the plum pudding model. And plum pudding was a type of pudding with raisins and different types of fruits scattered around, and with no set place. And what it represented is the custard in the pudding would be the positive amorphous blob of nothingness. And not nothingness. And the electrons are the negative charges scattered throughout, which are the raisins in this case. The plum pudding model of an atom was an amorphous shapeless blob of positiveness with some negative charges distributed throughout. And this is another depiction of his model. I set up an experiment to test this model since I was curious to see if I could prove or disprove anything about it. So I set up the now famous gold foil experiment. I proposed that if I shot alpha particles, as you may recall, those are positive particles, through an atomic structure, they would pass right through undisturbed, as if you were shooting bullets through snow. This is what I thought would happen under J.J. Thomson's model. So I made an alpha emitter, or gun, which was a piece of uranium encased inside lead with an opening, so the alpha particles could get out of the lead, or be emitted. So I shot alpha particles through a hanging piece of gold foil. This gold foil was 6 × 10⁻⁷ meters thick, That's really, 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 really thin. That is 0.6 zeros and a 6 meters, or 0.6 microns. An alpha particle detector screen was surrounding the gold foil, and to detect where the particles hit the screen after going through the gold foil. I worked with a smart man called Hans Geiger, who is the inventor of the Geiger counter, which measures radioactivity in the area. Here's a depiction of what I did in my experiment of the gold foil experiment. As you can see, the blue is the detecting screen. There's the slit where the alpha particles can get through and hit the gold foil. But as you can see, what I found did not support J.J. Thomson's model, that they would just pass through undisturbed. Some were deflected a little bit, and 1 out of every 8,000 were deflected almost directly back where they came from. But most, 99.99% of the alpha particles shot right through the gold foil as if it wasn't there. And this is what I thought an atom looked like after conducting this experiment. A positively charged center carried a field of negative charges that were scattered around it. And as you can see in this picture, it shows that the alpha particles actually hit the nucleus, but that's incorrect. That's just how they showed it. Because really what happened was it was simply deflected, positive on positive, like when you try to stick magnets together. So I mathematically calculated that the atom was mostly empty space, and that's a very important piece of information. So I concluded that the diameter of the nucleus is 1/10,000th the diameter of the atom. For example, stand in the middle of Turner Field and place a baseball in the center representing the nucleus. The electrons would be outside of the stadium. In between is empty space. If you stood in the field with a baseball representing the nucleus of an atom, then the closest electrons would be half a mile away. That's far. And like I said, the area between them is empty space. Think of steel or concrete or any substance, or the floor that I'm standing on. In an atomic level, it's made up mostly of empty space. It's a hard concept to grasp, I know, but an atom is made up mostly of empty space. This is what was happening on the atomic level of everything. This was the experiment that mapped out the atom known today. The gold foil experiment opened the door to quantum physics and the advances that we have today. So electrons are orbiting at a distance from the nucleus in an area which we call shells. Now they're not really orbiting, they're just scattered around in an erratic way, not in any way similar to the way our planets orbit around the center of our solar system, the sun. And I made a model of this picture, and it is 2 positive charges, or protons, and 2 neutral charges, or neutrons, and the electrons just scatter around in no defined orbit around the nucleus of the atom. Moving on from that, unfortunately, I died on October 19th, 1937. And I was only 66 years old, and I died from a complication of a simple surgery to remove a hernia. Now, the Nobel Prize. The Nobel Prize is recognized as one of the most prestigious awards given for intellectual achievement in the world. The recipients are awarded with $1.3 million US and a 24-karat gold medal, which is depicted there. This was set up by Alfred Nobel, whose face is on the medal, a Swedish chemist, an engineer, inventor, an armaments manufacture. Ornaments are bullets and weaponry items of that sort. There are 6 categories the prize is given in: physics, chemistry, medicine, literature, economic science, and peace. Alfred Nobel had 355 patents or invention rights, and the most significant was dynamite. Alfred Nobel became very rich before he died, and in his last will and testament in 1895, he drafted the organization. The first prize was given in 1901. Now annually, the prizes are given by the Swedish king on the anniversary of Alfred Nobel's death in December 10th. I hope you enjoyed my presentation, and thank you for watching. But here are some citations that you can look at to explore more about me and learn more about me. Thank you.